Good afternoon, friends. I hope you're all doing quite well. Wanted to spend a little time with you looking at discrete structures. Let's go ahead and get the screen shared and see what we're working on this week. Okay, so hopefully right now you're seeing the course summary and looking at Monday, February 22nd. This is when our homework 5 discussion was going to be coming up on us. So I've got that open up. We've got several sections to cover and only a couple of problems each. So we're going to briefly discuss this here for a few minutes. All right. You still have the normal criteria. So if you struggle with any of these problems, you could fall back on the normal criteria. So it says 5.1, 5, and 6. Let's go see what those questions are. Whoops, need this here. 5.1, 5, and 6. Okay, prove that 1 squared plus 1 squared plus 3 squared plus 5 squared plus 2n plus 1 squared is equal to n plus 1 times 2n plus 1 plus 2n plus 3 divided by 3 whenever n is a non-negative integer. Okay, so on these proofs, typically there's going to be a template that you can follow in the text. Let's see. But, oh, here we go. Gotcha. So let's just see what they have in the back of the book on this one. Okay. 5.1, problem 5. So this is, I think, a recursive proof. We'll find out. Did I miss it? 5.1, there we go. Question number 5. Let P of n be that, okay, so this is what we're going to try to prove. So the basis step is P of 0 is true. So P of 0 is going to be 0 or 1 squared, which is equal to 1, which is equal to all of these other things. Now the inductive step is now we have to assume that P of k is true. So this step says 1 squared, 3 squared on through is equal to k. Now, what they show here is that you can do some factoring out, some math trickery, and a little more math trickery and a little more math trickery. And so finally you get this. And so this is somehow supposed to be the same thing that you have up here. And so that works. Now, problem number 6. We'll go with this. I guess I don't have my... There's 5.1 and number 6. So in the basis step, let's read. What is problem number 6 right quick? 6 is going to be prove that 1 times 1 factorial plus 2 times 2 factorial plus through n times n factorial is equivalent to n plus 1 factorial minus 1 whenever n is a positive integer. Okay, so our basis step is 1 times 1 factorial is equal to 2 factorial minus 1. Okay, so 1 factorial is 1. 1 times 1 is going to be 1. 2 factorial is 2 times 1, which is 2, minus 1 is 1. So 1 equals 1. Yay! Assuming the inductive hypothesis, we have the inductive hypothesis, which shows we stop off at that middle step, which is k. And so we do some math trickery, and we see that this little nugget, k plus 1 factorial, is k2 factorial minus 1. And so everything kind of lines up and everything ends up working out nicely. Okay, there's some serious hand waving there, but it's an algebra trick to get from step A to step B. And so if you struggle with that, you can just write that down for your work. It's not great, but you can at least get through it. Go slowly and it'll help. The rest you should be able to hopefully work out on your own. Okay, let's move on to 5.2, problems 10 and 11. So 5.2, 10. It says, assume that a chocolate bar consists of n squares arranged in a rectangular pattern. The entire bar, a smaller rectangular piece of the bar, can be broken along vertical and horizontal lines separating squares. Assume that only one piece can be broken at a time. Determine how many breaks you must successively make to break the bar into n separate squares. Use strong induction to prove your answer. Okay, so let's go back 5.2, number 10. All right. In performing the inductive steps, it really does not matter what letter we use. We see the use of P of J and K, but it would just be as valid to use the others like J and N. Since K is the first case and N is the second case, are just dummy variables. Blah, blah, blah. Okay, so a claim it takes exactly N minus 1 breaks to separate a bar or any connected piece of a bar by horizontal or vertical breaks into N pieces. We use strong induction. If n equals 1, this is trivially true. One piece, no breaks. Assume the strong inductive hypothesis that the statement is true for breaking into k or fewer pieces, and consider the task of obtaining k plus 1 pieces. We must show that it takes exactly k breaks. The process must start with a break, leaving 2 smaller pieces, and we can view the rest of the process as breaking one of the pieces into I plus 1 pieces and breaking the other into k minus I pieces for some I between 0 and k minus 1 inclusive. By inductive hypothesis, it will take exactly I breaks to handle the first piece, breaks to handle the second piece. Therefore, the total number of breaks will be I, 1 plus I plus k minus I minus 1. Now, the minus 1 and the plus 1 cancel each other out. The minus 1 or minus I and the plus I cancel out. And so we're left with k as desired. So that's pretty handy. Okay, so let's take a step back. Whoops, nope, wrong one. We're going to pop over here and we'll look at 11. Consider this variation on the game NIM. The game ends with N matches. 2 players take turns removing matches. 1, 2, 3 at a time. The player removing the last match loses. Use strong induction to show that if each player plays the best strategy possible for the first player wins if n equals 4j, 4j plus 2, or 4j plus 3 for some non-negative integer j. And the second player wins in the remaining case for some. Okay, so I thought it looked like fun because it was a game, but it's not that fun of a game. So we'll bounce over here, and this is 5.2, problem 11. So we scroll down, 5.1 answers were long. Here we see 5.2, and here we see problem 11. And so the basis step, there are 4 base cases, n equals 1 or 4 times 0 plus 1, then clearly the second player wins. If there are 2, 3, or 4 matches, then the first player can win by removing all but one match. Inductive step. Okay. Assume the strong inductive hypothesis for k or fewer matches, and the second player, suppose we have a game with k plus 1 matches, and there's that modulo operator again. The first player can remove 3 matches, leaving k minus 2, because k minus 2 modulo is congruent to 1 modulo 4 by inductive hypothesis, second player. All right. So it is a bit of writing, but the idea here is this is a different way of working through these problems. Okay. These aren't great examples, but this is one way to work through proofs. And it's basically showing you have the base case, and then you have the inductive step, and then you have strong induction. Okay. Moving on, let's look at our next problem. We've got problem 5, section 5.3, problem 7 and 8. Okay, so I want to stay on this tab. 5.378. So give a recursive definition of the sequence of a for n equals 1, 2, 3 if a of n is equal 6n. Okay, so this is one of those where it's very beneficial to slow down and just use pencil and paper and try to think about it. So if a of 1 is equal to 6, and then a of n plus 1 is equal to 6 plus a of n. That'll give us kind of a recursive way to do that. So let's go see if that's what they had. So it's 5.3 question 7. So let's roll down to find that. Okay, so 5.3, there's question 7. They're going to give the relatively simple answers. So this is a sub 1 equals 6, and a sub n plus 1 is a sub n plus 6. And so every number it's just going to advance by 6. So that's kind of what we had talked about. Okay, B, a sub n is equal to 2n plus 1. So let's do a case of n equals 1 first. So a sub 1 is equal to 2 plus 1, which is 3. So a sub 1 equals 3. And then we're going to do a sub n plus 1 is equal to 2a sub 1, 2a sub n plus 1. Yeah, I think it'll be 2 times a sub n plus 1, and a sub 1 equals 3. So let's see if that's what they have. So 2 plus a sub n and a sub 1 equals 3. So it's a sub n plus 2. Yeah, I was a little bit off. Okay, so the next one, a sub 1 equals 10. A sub n plus 1 is going to be equal to 10 times a sub n. So let's see, 10 times a sub n, a sub 1 equals 10. Okay, all right, now let's take a look at D. A sub n equals 5. Well, this is fun. The recursive definition of this is a sub n, I don't know how I'll do this one for sure. D, a sub n plus 1 equals a sub n, and a sub 1 equals 5. Okay, so that's how you do that. Okay, problem number 8. It says give a definition for these sequences. And so notice there's some strong similarities. Hopefully you'll start to see some patterns that are showing up. So we come down here, 5.3, number 8. So this one was a sub n equals 4n minus 2. So for a sub 1, this is going to be 4 minus 2, which is going to be 2. So a sub 1 equals 2. A sub 2 is going to be 4 times 2, which is 8, minus 2, which is 6. So I think that'll just be a sub n plus 1 equals 4 plus a sub n, and a sub 1 equals 2. So let's find out if that's what I said. A of n plus 1 is a of n plus 4. Yep, a of 1 equals 2. Okay, so that is what we said. All right, and we're going to follow a similar pattern for all of these, where we're going to try to take a guess. If our guess is right, great. Otherwise, we'll be okay. Let's go back and let's look at the homework again. 5.4, 8, and 9. 1 second. This one says give a recursive algorithm for computing n of x whenever n is a positive integer and x is an integer using just addition. Is that the right one? Nope, 8 and 9. Oh, 1 second. Dancing in the Moonlight by King's Harvest. One of my favorite songs, and also a gentle reminder that it is time for me to step away here relatively soon. So 8 and 9, recursive algorithm for finding a sum of the first n positive integers. There's actually a closed form for this, but we'll use a recursive form. So this is problem 8. So that's going to be here. So 5.4, problem 8. So here you go. The sum of n positive integers is n minus 1 positive integers plus n. Trivial observation leads to the recursive algorithm shown. Sum of n positive integers, if n equals 1, return n, else return sum of first n minus 1 plus n. Okay. And then problem 9, algorithm for finding the sum in odd. So this one's going to be slightly different, if I remember this correctly. So 5.4, problem 9. Yeah, it's slightly different, right? Because we've got to do sum of odds n minus 1 plus 2n minus 1. And so it's got to skip a few numbers. So it goes just a little bit faster. And then 5.5, 7, and 12. Okay, now 5.5, 7, and 12. So 7 Fibonacci numbers. And this one we've actually covered in a different video. If n is 1, return 1. If n is 0, return 0. Else it's n minus 1 plus n minus 2. And so Fibonacci numbers, yeah, 5.5, question 7. 5.5, question 7. So it has an answer, but it's not great. And then the other question was question 12. Describe a recursive algorithm for computing greatest common divisor for two positives. Okay, for this one, we'll pop over here. It says, suppose the initial assertion is true. So anyway, these problems can be a little bit daunting. They're a little hard to work through, and some of the times, basically what we have to do is just say, okay, let's see what the book had to say, and then we kind of build our own understanding based off of what the book has provided for us. The goal of these problems is just to kind of get you to think about, okay, how do we do things in a different way? And an example of this way of thinking is, today I was in the surfer closet. I was trying to connect a system called iDRAX. So it's integrated Dell recovery environment command center or something like. Anyway, iDRAX is something that we use to control things like Pixie booting, which is where instead of your operating system coming from a local hard drive, it goes to an IP address and then pulls the operating system down from there and then loads that into memory. Anyway, it's great for system administration. But before we could do that, we're like, well, do we even know that we can talk to this switch? So, or this IP address. So we went in with a Raspberry Pi and we got the base case going, if you will, which is, can we connect to a Raspberry Pi over this switch using this configuration? And we could. And next week we'll be starting on the iterative step, which is trying to connect iDRAX into that IP address across the unmanaged switch. So anyway, friends, it's a different way of thinking about problems. Don't stress about it too much. Do the best you can. If you have to refer strongly and lean strongly on the solutions provided, I'm okay with that. But it is an interesting way of thinking about solving problems, and it's something that not everybody has seen before, and so I do enjoy it. Anyway, I'm going to go ahead and stop my share. Thanks again for spending some time with me. I hope you're doing well. I look forward to getting a chance to slow down things a little bit and get a little more into a normal routine. Last week we canceled school all week for a snowstorm, so hopefully this week we have a little more time. Thank you all again for your time. Have a wonderful day, and please do let me know via Discord, email, or Canvas if there's anything I could do to help you be more successful. Thanks and take care, friends. Bye.